way to do this is you have your compliance matrix that, tell me if anyone disagrees with this, but I got 6.99 times 10 to the minus 7, negative 3.5 times 10 to the minus 7, negative 3.5 times 10 to the minus 7, and then zeros. And then I got negative 3.5 times 10 to the minus 7, 6.99 times 10 to the minus 7, negative 3.5 times 10 to the minus 7, and zeros. And then minus 3.5, minus 3.5, positive 6.99, and zeros. Is that what everybody got? And then now we go down to the rows that only have elements in the shear positions. So 2.1 times 10 to the minus 6, and zeros. And then this just keeps moving along the diagonal. And to come up with the strain now, the Voigt strain is equal to that C matrix times the stress tensor, which looks like, or not the stress tensor, sorry, the Voigt form of the stress. So we have a X stress of positive 7.5 E3. The YY stress, this is compression, so this should be negative 5.55 E4. Z is 0, and that's why this is called, well, the reason this is called plane stress is that all the stresses that are non-zero act in one plane. So we're not going to have any Z elements for anything. And so we have 0 for the YZ shear stress, 0 for the XZ shear stress, and then 1.5 times 10 to the 4. And notice that this is pointed in the, so if you look at like the X face, this is pointing in the negative Y direction. So that's going to be a negative stress of 1.5 times 10 to the 4. And if you do that multiplication, you get a stress of 0.024, sorry, a strain of 0.024, negative 0.041, positive 0.016, then 0, 0, negative 0.032. Okay, so what do we see here? There's one thing I think that's worth noticing. We have a state of plane stress, but not a state of plane strain. Even though there's no ZZ normal stress, there is a ZZ normal strain, and that comes from the Poisson's effect. Okay, so even though we're not applying any stress in the Z direction, the thing you can think of it as we're getting a net expansion in the Z direction that comes from these other normal stresses. And then there's no thing similar to the Poisson's effect when you're talking about shears. If you look at this matrix, the only thing that determines one particular shear strain is that particular shear stress. That's what it means that all you have in this box is diagonal elements. So the only thing that can produce a YZ The only thing that can produce a YZ strain is a YZ stress. The only thing that can produce an XZ strain is an XZ stress. Okay, and so on. Yep. Yeah. Okay. Okay. So the definition of the normal stress is it's the, so you can think of every face. So remember the cube. Every face has potentially 3 components acting on it. So you could have this, and this acting on this face. And you can think of those 3 components as adding up to a vector. Okay. The normal stress is the one that's perpendicular to the face, and that's equivalent to this 7.5 E3. If it's going out of the face, the sign convention says that that's positive. If it's going into the face, it's negative. So tension is always positive, compression is always negative. Okay? And then the other, any questions about that? Does that make sense? Then the other 2, the signs come from, so this is the component that's on the positive X face in the Y direction. If it was pointed down, it would still be the Y component on the X face, but it would be negative because it would be pointed in the direction of the negative Y axis. Okay, so that's what's happening here. The shear stress on the positive X face parallel to the Y axis is in the negative Y direction. Okay, so that's how you come up with those signs. Any other questions? So that's all there is to the constitutive relationship. Between stress and strain. So now, if we can come up with a stress, we can come up with the strain no matter what the state is, as long as our assumptions are met. So now all we have to do is come up with ways to figure out what actual strains are. You know, like when you look at an engineering structure, it doesn't look like an infinitesimal cube. So how do we go from these macroscopic bodies to this stress state? And then once we have that stress state, we just multiply by this matrix to get the state of strain. So we're going to start out with the simplest case. So let me write something like that down. So now we just need to know how to determine the stress states. So we're going to start with uniaxial tension and compression. You treat these 2 the same way. In prismatic bars. Prismatic means that the cross section is the same the whole way along the length. And bar means much longer than wide. So, for example, we could deal with, most often we'd have something that looks like this. But we could also deal with things that look like this, as long as the whole way down the cross section is the same. So if you look at this point, the cross section is the same as it was at the ends. Okay, so consider tension first. And we'll deal with states where we think of this bar as having distributed loads applied at the ends. And these distributed loads add up to a load P, to a force P. So first, you have to choose a coordinate system. And just by convention, we're always going to choose a coordinate system with the x-axis pointing along the length. So it's along the long axis of the bar. And then at every point, this is the big leap. At every point in the bar, it turns out that the axial stress, the normal stress, is what your first guess would be. And that is that it's equal to, hold on a sec, froze. Well, what would you guess that the stress is going to be? How would you calculate the stress given? So let me give you a hint, I guess. Let's say that the cross-sectional area at any point has a value of A. How would you calculate the stress? It's the same way we did it in the mechanical test of the rubber band. Yeah, P over A, right. I might just have to do this on the board. Okay, so then the axial stress is equal to P over A. Everything else is 0. So if we wanted to draw the stress cube representing this, we'd have an x normal stress of P over A. Would be on the other side too to keep it in equilibrium. Zeros everywhere else. And so you get a stress tensor of P over A, 0, 0, zeros everywhere else. And then the Voigt stress would be P over A, 0, 0, 0, 0, 0. In a state like this, what would you expect the strain to look like? So you don't have to give me numbers, but what do you expect so in this direction, it's going to be stretched along the x-axis. So you're going to get a positive xx strain. And then there'll be two other non-zero values. That'll be in the y direction and the z direction, you'll have the Poisson's effect, and those will be compressed, contracted. Okay. Okay, so let's say that we have a bar with a total force of 20,000 newtons. And a cross-sectional area of 0.003 meters squared. And let's say that this is steel. Which means that you have an E value of 200 times 10 to the 9th pascals, and a Poisson's ratio of 0.3. So first, calculate the stress tensor at every point. And second, calculate the strain at every point. So why don't you guys take a few minutes and work on that?